You know, there one time 2 years ago, Lucas Ball sat right here, and he developed an intro to all of my videos. So he would like, "Welcome back, everybody. This is Calculus." So that's your task.
What? Okay.
Yeah, let's go down.
I'm not gonna put you on the spot. You don't have to do it right now, but
All right. I gotta rehearse it.
Yeah,
You gotta reverse.
Yeah. All right, ladies and gentlemen. So let's get into section 1, 2. Yesterday I was talking about the different types of models that we could have. Right. Basically, a model is just an equation that we can come up with to model a situation, right? Whether we had, this was the temperature versus height graph that we had. This was a formula we created using y equals mx plus b to model the situation. But we said, well, life isn't always as easy as just getting 2 points and making a line. What happens if this line maybe deviates a little bit away? Well, that we can create an empirical model for that. And we said that's like using regression analysis, and we can, we did this regression analysis based on the Mauna Loa Observatory in Hawaii, right? It was funny in my 7th period class, because we had seen that the results came out a little bit wacky than we thought it was going to in 2022 or whatever it was, right? The linear model actually wasn't a really good fit. We saw that it was like something like 420 parts per million, when our model said it was only going to be like 408 or 409 or something like that. So I actually ran a quadratic regression to see maybe this wasn't linear, but maybe this is quadratic. Maybe this is growing at like an x squared pattern, and that was closer than our linear model came out to be. Just interesting. I don't know why I found that interesting, but all right. So the rest of this lesson is just going to talk about the different types of functions that we could possibly have. Now, I'm not expecting you to write down everything that we have on this screen. Again, your notes are your notes. You can write down whatever you want, but we're going to go through all the different types of functions that we will see this year. Okay, back in Algebra 2, that was like the beginning of studying all different types of functions. Basically, we took it chapter by chapter and said, okay, these are the different types of functions that you could possibly see. All the different types. And by the end of Algebra 2, you saw all the different types of functions that there are. So we started with linear, and now we're going to talk about polynomial. Polynomial functions, we're going to work a lot with polynomial functions. The rules for calculus are very easily demonstrated through polynomial functions. So we're going to be using polynomial functions to see, okay, what does a derivative look like? What does an integral look like with polynomial functions? And each of the different types of functions kind of have their own rules and things to use. And polynomials are really straightforward. We're going to be working with those a lot. But what is a polynomial? Basically, it's just we have a degree. That degree is the highest power on any of the variables. Standard form is going in descending order in terms of degree as we write the equation. And we just have to have positive integer, I'll say whole number exponents, right? Whole number exponents. And we can have coefficients on those. Those could be really anything that we wanted, though. The coefficients on the variables could be positive, negative, rational, irrational, doesn't really matter. The domain of any polynomial is always all real numbers. The range kind of depends on what the function looks like, what the degree is, whether it's opening upward, downward, whatever it may be. But the domain, I could plug in whatever I wanted. Like think about just a plain old x squared. It doesn't matter. I could plug in anything. I could square any number, and I don't have any restrictions on that. Okay, this example is a polynomial of degree 6. And we know a lot of things, and in Algebra 2 we studied a lot of the things that we know based on the degree and the leading coefficient and whatnot. And we discussed end behavior. If you had me, we did the end behavior dance. Did anybody? We either had Mrs. Napoltz or me for Algebra 2, right? Did anybody have Mr. Hudson for Algebra 2?
Yeah.
Yeah? Because he taught it 1 year, and I was thinking that it might have been this year. Did you have Hudson for Algebra 2?
Yeah, I had Naples, and I had Hudson, and then I had BLF, and I had BF.
Ah, that's cool. Okay, cool. All right. So anyway, but if you had me, we did the end behavior dance, and we'll talk about that a little bit more later on. Okay. So more basic forms of polynomial functions are quadratic functions. Quadratic functions just have a degree of 2. Cubic functions have a degree of 3. You could say quartic functions have a degree of 4. Quintic has a degree of 5. But once we get beyond 5, there's no real names for them. Polynomial degree of 1. Actually, a linear function is actually polynomial. It's just a type of polynomial equation that has a degree of 1. And we can write it as mx plus b. So yeah, linear functions are polynomial. We don't really consider it that much, but yep, it is. Quadratic functions are polynomial. Cubic functions are polynomial. X squareds, x cubeds, whatever it may be. We know parabolas open upward if my leading coefficient is positive. Parabolas open downward if my leading coefficient is negative. Polynomial of degree 3 would be a cubic function, and it kind of looks like that guy right there. There's a polynomial. There's a cubic function. We'll talk a lot more about these. This is just showing some examples. That's a cubic. This would be a quartic. This would be a quintic. Things to remember there that if you have a degree of 3, you're going to see 2 changes in direction. Right? It's going up, down. Actually, we're going to see 2. We're going to call these maximum and minimum points. Right? 2 maximum or minimum points. It's going to go up, down, up. Right? If it starts up, it's going to turn down once. And then go second up. Right? 2 changes in direction. If you look at the quartic model there, the quartic equation here, you see 1, 2, 3 changes in direction. If you look at the quintic model, 1, 2, 3, 4 changes in direction. So it's always n minus 1 changes in direction. What else do I have to say about that? I can also, is this the time where I want to talk about end behavior? Sure. Remember that for end behavior, it always depends on the degree and the number and the leading coefficient. So if I'm thinking about the degree of this cubic, the degree is 3, right? If it's an odd degree polynomial, the end behavior is going to be different. One's going to go up, one's going to go down. Okay, and it depends on the leading coefficient, whether it's positive or negative. If it's even, they're both either going to go up or they're both either going to go down. If it's positive leading coefficient, they're going to go up. If it's negative leading coefficient, they're going to go down. So I created the end behavior dance. So we have this is positive even, this is negative even, this is positive odd, this is negative odd. So positive even, they're both going to go up. Negative even, they're both going to go down. Positive even, right arm's going to go up, left arm's going to go down. That means end behavior. See, this is example C here is a positive even. Positive leading coefficient, or sorry, positive odd, excuse me. Positive odd, 5 is odd. Positive negative, positive, positive odd. So right arm is going to go up, left arm is going to go down. So we see up on the right, down on the left. Now, what happens in between? That's what we'll use calculus to figure out what happens in between. But the end behavior, right arm's going to go up, left arm's going to go down. So it's going to keep going forever up and forever downward. Okay. Any odd degree polynomial, the range is going to be all real numbers. Any even degree polynomial, well, it kind of depends on where the lowest or highest point may be. Okay. All right. So we did this back in Algebra 2. Let's run a quadratic regression based on this. Okay. A ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. And its height h above the ground is recorded at 1 second intervals in this table. Find a model to fit the data and use the model to predict at the time at which the ball will hit the ground. I kind of let the cat out of the bag that it's going to be quadratic, but we're going to look at the other types too. So why don't we go ahead and get out our calculators and actually plug in this data. I'll make this table a little bit bigger. I'll shrink it down in a second. And let me pull up my calculator as well. Remember when you're, come on, there you go, buddy. Remember when you're clearing your lists, you go stat edit. Don't hit delete because your list will go away. We always say like, oh, don't hit delete. Your list is going to go away. It's going to be bad. If you delete a list, look, delete, it's gone. Oh no. You only have to do stat and then setup editor. And just run that, and then they're there now. It's back again. So if you delete your list, that's how you get it back. Setup editor, click done, boom, back. If you need to clear that, you highlight list 1, clear down. Highlight list 2, clear down. And it removes everything out of there. Okay, so we got 0 to 9 on our table 1. 0 to 9. And then we have our heights. I think we can see from the table that things aren't happening in a linear motion, are they? I decrease 5, then I decrease 14, then I decrease 23. So I'm the amount of which I decrease, the rate of change of my height is increasing, right? The slope as I continue is increasing from point to point, which is a key indication of it's not linear, it must be quadratic or something like that. Okay. So let's figure out what model is going to be the best. And how do I do that? I look at the R value for any of the models here. I'm going to go stat, calc. Heck, let's run linear. Why not? It's good to run linear because what is my R value? 0.5, negative 0.5. Good model? No. Do we all get the same values? No? Uh-oh, did I plug in something in my table wrong? Uh-oh. Yeah. Oh, 45. Whoa. Apparently I was typing too fast. 431, 408, 378. The calculator couldn't keep up with me. 332, not 32. I'm going to blame the calculator. It's the calculator's fault. Okay, here we go. Let's run that again. Stat, calc, 4. Okay. That actually looks like a really good model, doesn't it? But we know better. We know that it's not going to be linear. We know that this is not going to actually fit a linear model. So let's see. Stat, calc. Let's try a quadratic model. We were at 0.92 for our R squared value, and now we're at 0.99. Pretty good model, right? Let's see what, we bring that over, kind of save that. Let's see what cubic looks like. Stat calc 6. 0.99. Ooh, do we have more 9s? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 4. Oh, cubic looks good too. I wonder what quartic looks like. Stat calc 7. Ooh, we keep getting better. Okay. You know, what the interesting point about this is if I run any of these regressions and I answer the questions based on this, the numbers that I get in the end, like predict, the final question here is predict the time at which the ball hits the ground. No matter what I'm going to use here, it's going to be probably very similar no matter what regression I use. I know, and those of you who have taken physics know that if you drop a ball, any sort of gravitational pull, that's quadratic, right? That's quadratic. That's what is it? What's the formula? Negative 16 t squared or negative 9.8 squared t squared plus how much you're throwing it by plus h or whatever it may be. That is acceleration pulling down due to gravity, right? And the acceleration pulling down due to gravity is quadratic. So I'm going to kind of cheat because I know prior knowledge here. And I'm going to say, let's use the quadratic regression. Because I know that the best model for dropping something or throwing something is quadratic. All right, let's do that. Now, I want to know when the ball is going to hit the ground. Am I asked an x value or a y value? Am I asked to find an x value or a y value? I'm asked to find an x, right? I'm asked to find a time. I'm asked to find what time will the ball hit the ground? What time will the ball be at 0 meters? There's a couple different ways to do this. I could do this very algebraically. Like, let me go back to my quadratic regression here, and I can say, well, here's my formula. F of x is equal to negative 4.9 x squared plus 0.96, I'm just rounding, x plus 449.36. Couple things to notice here. That number, very similar to that number, right? Think about the y-intercept. Right? The y-intercept is going to be the starting value, 450. Those of you in physics, isn't that half of 9.8? 4.9? Right? Is that half of 9.8? And those of you recognize 9.8 as the acceleration due to gravity in meters per second squared. We're going to be working with a lot of like physics examples. Okay, but here's our equation. What I really want to know is this, right? When is height going to be 0? When is the output? When is the y value going to be 0? I don't know why I rewrote this whole thing. I could have just erased that and wrote 0. That's okay. And how do I solve that algebraically? Well, the easiest method to do is probably the quadratic formula. I got some messy decimals, but whatever. I could do that, right? Opposite of v plus or minus square root of v squared minus 4ac all over 2a, right? Negative 0.96, opposite of v plus or minus the square root of b squared, 0.96 squared, minus 4ac, all divided by 2a. Just messy decimals, right? I can do that. But we actually learned way back in Algebra 2 how to solve that without needing to use the quadratic formula. Everybody go with me here. Do this together. Do this with me in your calculator. I need to rerun the quadratic regression because it needs to be the last regression that I've ran. So I'm going to rerun the quadratic regression. This is the last regression that's stored in my calculator. Everybody hit your y equals. And you're going to hit vars, that VARS button, variable statistics. Scroll down to statistics, choice 5. Select that. And then 2 to the right is EQ. There's your regression equation. And you hit enter, and it should put it into your y equals. Let me run that again. Let me show you that again. Clear that out. It's got to be the last regression that you ran. You go vars. When you're in y equals, you got to go vars, statistics, choice 5, and EQ to get to your regression equation. Okay, so there is my equation in. I can also plot my list 1 and my list 2. Everybody go up to plot 1 and highlight it. Hit enter on it. Now, if you want to see what plot 1 is doing, you can get into that by doing second y equals and seeing what your stat plots are. It says plot 1 is on, and I can even go so far as to click into plot 1 and say, okay, I'm just going to make it be points. I could make it be a histogram or a line graph or a box and whisker plot, whatever it may be. But I want to use list 1 and list 2. But I'm going to turn on that stat plot. Now I'm going to zoom. Choice 0 for me is zoom, or sorry, choice 9 is zoom stat. Zoom stat, zoom 9. And we see our points in there, and we see our curve. Now the nice thing is what am I gonna look for here? I'm looking for the 0 of that function, aren't I'm looking for when does the ball hit the ground again? What is the value when it hits that x-axis? So I can hit second calculate 0. I'm going to calculate my 0. Now it's going to ask me left bound, right bound. So I just do somewhere to the left. Click. I've got to do somewhere to the right, which I need all the way back down here. And then guess somewhere in the middle. But there it is. And then when I hit enter, 9.67 seconds. 9.67 seconds. I wonder how close, like if I run this, I wonder how close we actually get to 9.67 seconds. I'm guessing it's just a little off because I had to round to 2 decimal places here. And when I put in my equation, my bars in my equation, it went to like a lot of decimal places, like 8 decimal places. So this is always going to be more exact when you do it in your calculator like that. Yes?
I'm sorry, but I got lost when you went to plot 1.
Okay, so we were here. So I lost you when I turned on plot 1. Did you turn on plot 1?
Yeah.
Okay, hit zoom. And then do zoom stack. Does it look like this? It should. It doesn't? Uh-oh.
Maybe I didn't.
Let me just check. Check.
I don't have that.
You are in.
What?
Did you guys do polar graphing at the end of the year last year with Mr. Dio? Yeah, you might be in polar coordinates. I'm gonna go back in here. There we go. There we
Should
go.
my intro.
Here, you know the nice thing that I gave you and Mrs. Napoltz gave you back in Algebra 2? Let me see if I still have it. When's the last time I taught Algebra 2? 2021 school year. Algebra 2. Algebra 2. Chapter... When did we do this? Chapter 2? No. Curve fitting with linear models. Maybe it's back here. Algebra 2, chapter 2. Okay. I will post this on Canvas if you'd like to. I think I actually have it uploaded on Canvas already. It's just not published yet. But way back when Mrs. Napoltz made this awesome Word document with screenshots of how to do all of that process. Okay. I remember I printed this out for you guys back in Algebra 2. But this is how she shows it using a linear model. But you could do this using any model, using a quadratic model, using a quartic, whatever it may be. Okay. But again, I'll publish this for you and put it on Canvas. Okay. But again, all of that process is will be on that sheet. Okay. So again, we're here. We've got our equation. To find our 0 again, I'm going to hit second calculate 0. I got to hit that. Oh man, it's got to go back to here. Left bound. I wanted to screenshot this. That's why. Come on. But again, you got to hit left bound and then right bound. You got to go somewhere to the left of your 0, somewhere to the right of your 0. Oh man, it's laggy. Oh, that's got a bunch of lag in it. Still going. Okay. And then it's just going to make you guess. So basically hit enter a couple of times. And there it is. 9.67 seconds. Okay. That is when the ball will fall. Ball will hit the ground. Okay. I can also use this and say, maybe somebody's standing, or maybe there's something at 175 feet off the ground, right? maybe there's something at 175 feet off the ground, and I want to know how long it's going to take that ball to reach 175 feet off the ground. To find that, I go y equals, and I say, okay, if the height is 175, and I want to know what the x value is going to be at 175, you can plot it. I don't know why all the way went down to y4. Doesn't matter. If I graph that, you're going to see a horizontal line running through at whatever y value you chose. And then to find when that's going to happen, you second calculate instead of a 0, you just find the intersection point between that horizontal line and the curve. So choice 5 there. Now it's going to ask first curve, second curve, guess. You can hit enter all the way past that. And so we know at 175 feet off the ground, it will take 7.58 seconds to reach that point. Okay, so you can find x values, you can find y values, whatever it may be. If you want to say, oh, okay, I want to know how high it is off the ground at 7.75 seconds. 7.75 seconds, well, that's an x value. You just second calculate value of 7.75. So 7.75, it would have been 162 feet off the ground. Okay. So you can find x values given y values. You can find y values given x values. Now this is the case for quadratic, cubic, quartic functions. Doesn't matter. All of these will work the exact same way. And again, if you need any of those instructions, I will post that Word document. All right. Now we don't actually have any more examples until we get to the very end. Oh, maybe there's one in the middle there. But these are all just other different types of functions that we could possibly have. So again, whatever you want to write down from this stuff, whatever you don't remember, whatever you do remember. Power functions are unique types of polynomials. Honestly, a power function, we don't really call them power functions back in Algebra 2/Pre-Calc, but it's just basically one where it's just a variable and an exponent. That's it. So it is a specific type of polynomial where it's just y equals x, or y equals x squared, or y equals x to the third, or y equals x to the fourth, or y equals x to the sixth, whatever it may be. Okay, there are a couple different options though. If your power is a positive integer, a whole number, a natural number, I guess I should say. You don't want it to be x to the 0. If your power is a natural number, 1, 2, 3, 4, 5, or whatever it may be, no decimals, then it just follows the same rules as just a polynomial. Same end behavior, all that stuff. You may be thinking, well, wait a sec, for the fourth power, we saw 3 changes in direction. Where did that go? We'll talk a little bit more about that. It just has a multiplicity in there. Okay. We talked about multiplicities back in Algebra 2 as well. If A is a fraction power, okay, if your power is fraction, then it actually turns into a root. It turns into a root. Remember, x to the 1 over n is the nth root of x. That's the rule for if you've got a fractional exponent. You've worked with those a ton, though. So like x to the 2/3 power would be the third root of x squared. The x to the 4/5 power is the 5th root of x to the 4th. Right? And then as commutative, I can take the 5th root of x raised to the 4th or the 5th root of x to the 4th. It doesn't matter there. You can change the order in a second. It could be any different. A couple things about this is whenever you have that x to the 1 over nth power and a fractional exponent, the domain is got to be greater than 0. For any even denominator things, right? Just like if we have a square root function or a 4th root or a 6th root, if it's even, you can't have any negatives underneath that radical. If it was odd, if the denominator was odd, then the domain is all real numbers. Okay. What happens if you take a power that's negative down to the denominator, right? So it'd be x to the negative first power is actually negative second power. It'd be 1 over x squared. X to the negative first is 1 over x, right? And that's when we started to get into rational functions. That was like the very first thing that we did. We said, okay, well, what happens if x is raised to the negative first power? And we had this inverse variation. 1 over x, our most basic hyperbola. Its graph is the equation y is equal to 1 over x, or xy equals 1. It's a hyperbola with the coordinate axis as its asymptotes. Remember, as soon as we start getting into rational functions, that brings out asymptotes. They could be horizontal asymptotes. There could be vertical asymptotes. There could be slant asymptotes as well. But again, we'll get into all sorts of different things in that. A lot of inverse variations come up here. Like this is, they give the example of having Boyle's law in here, V is equal to C over P, basically volume of a gas formula. Power functions are also used to model species area relationships. We'll talk about more in some of those exercises. I don't need to talk about that right now. But again, power functions are just a unique type of polynomial where the exponent may get just a little funky. Where we have a negative exponent where it's moving down into the denominator, or a fractional exponent where it's actually a root. Okay. Other types of functions that we may see along the way, rational functions. Rational functions where P over Q is, P of X over Q of X, where P and Q are both polynomial. Okay. A rational function is just basically a ratio of two polynomials. A ratio of two polynomial functions. We will work a lot with rational functions. Like I said yesterday when going over the homework, you're going to find that the rational functions are usually the weird ones. The ones that kind of have special rules and special things to make note of, like domains and things like that. You got to watch out for rational functions. This is just an example of a rational function down below. 2x to the fourth minus x squared plus 1 divided by x squared minus 4. We're going to be graphing these by hand eventually. We're going to be, we're going to have some major fun with that stuff. We've got to remember the rules for asymptotes there. Remember, there's rules for asymptotes with rational functions where if it's top heavy, meaning if the degree on the top is bigger than the degree on the bottom, there are no horizontal asymptotes. If the degree on the bottom is bigger than the degree on the top, then the asymptote is at 0. If the degree on the top is equal to the degree on the bottom, then it depends on what the leading coefficients are, where that goes. We'll talk about that a little bit later on too. And there are slant asymptotes as well. Okay, there are slant asymptotes as well. That's when the degrees match up as well. But again, those are rational functions. We'll talk a lot more about those later on. And then we have this idea. Did I skip trigonometric? Oh, I guess it does algebraic before trigonometric. Doesn't matter. Algebraic. Now this is kind of like a weird one. This is kind of like a catch-all. It's saying if you have a combination of any of these things, you can just call it what's known as an algebraic function. Okay. A function f is called algebraic if it can be constructed using algebraic operations with other types of functions. So if you have addition, subtraction, multiplication, division, or taking roots of different types of functions, then you could call it an algebraic function. Like for example here, this is like f of x is a polynomial inside a root, right? Two different types of functions happening at the same time. It's almost like a composite. Where there's like one inside the other. That would be considered by our book standard an algebraic function. Again, it's kind of like a catch-all, one that if you have a bunch of different types of functions happening at once, that's an algebraic. This is like a root function inside a rational function with a polynomial multiplied by a root. All different types of functions going on. It seems like a really weird one going on in G of X. A lot of different things happening. Well, then that's just called an algebraic function. Chapter 4, we will learn how to graph any of these. That's why I say chapter 4 might be a little bit more on the difficult side because we will graph all of these from scratch. And we have to think about all the different types of rules that we have. These are just different types of algebraic functions that we have. Okay. Different examples of them. And then we have our good friends, the trigonometric functions. The trigonometric functions are basically just sines, cosines, tangents, secant, cosecant, cotangent, all those fun things. Trigonometry and the trigonometric functions. Make sure that we're always in radian mode. The convention is out that we are always in radian mode, except when otherwise indicated, obviously. Okay. You studied this a lot in pre-calc, right? Learn how to graph sines, cosines, tangents, where their periods are, where their amplitudes are, what their when they, start repeating, right, where their zeros are. How do you stretch them? How do you shrink them? But this is the graph of sine of x and the graph of cosine of x. A couple things to make note of. Notice that for both the sine and cosine functions, the domain is all real numbers, right? Doesn't matter what I plug in to sine or cosine, I'm going to get something back out again. But the range is bounded, right? It's bound by -1 to +1. And this is just for basic sine x, cosine x. I know we can do things to it to make that amplitude a little bit bigger and change the range. But for our purposes here, when just looking at the parent sine and cosine, the range is between -1 and +1. Okay. Now for tangent, that's different. Tangent, that is very different. It's its own kind of thing there. An important property of sine and cosine functions is that they are what's called as periodic. Remember, sines, cosines, and even tangents have the period where they will start to repeat over again. And remember, we can do rotations of 2 pi. If you add on 2 pi to any radian measures, so like 0, 2 pi, 4 pi, 6 pi, 8 pi, and keep that rotation going on and on and on again, I should be getting the same sine value as the original, you can call it the reference angle. Right? That goes for sine and cosine and tangent as well. Yeah, but it's a good idea to just remember that you have those rotations, because that's going to come up right here. One of the other examples that we have, what is the domain of this function? What is the domain of this function? So I would consider this an algebraic function. Why? Because I see a rational function with a trigonometric inside of it. Now, when I ask you for the domain of an algebraic function, you have to kind of think of it like you would like a composite function, where you say, okay, I've got two things going on in here. I've got to apply both sets of rules to my domain. Like, for example, here, are there any restrictions on the domain of cosine? Like, are there any restrictions on what I plug into cosine? No. There are restrictions on what I get out. I can only go from -1 to +1 on my range, but no restrictions on my domain. Are there restrictions on the domain of a rational? Yes. I do have restrictions on the domain of a rational. I have to say 1 minus 2 cosine x cannot be 0. I have to say the denominator cannot be 0. So I have to figure out when this is happening so that I can truly see what the domain is going to be. So let's just solve that equation for x. I subtract, actually let's just add cosine x over to the other side. 1 is not equal to 2 cosine x. Divide by 2, 1/2 cosine x. And then I'm basically going to solve this. Inverse cosine of 1/2 is this. Okay, without our calculators, what is the inverse cosine of 1/2? What is the inverse cosine of 1/2? Now, you got to think about it this way. You're looking for the angle, right? You're looking for the angle that has the x or y value. Which one? X or y value? X value. You're looking at the angle that has the x value of 1/2. Anybody remember what that is? Ooh, you guys are good. In radians, what would that be? Pi over 3. Pi over 3. Anywhere else? Yes. Now remember, okay, so if it's the 60 degree, where else has that same x value? Down here, right? Right? If you're thinking about the unit circle, where else has that same x value? Ooh, that's not a circle. It's down there. Okay, so what is that? 300, right? In radians, what would that be? 5 pi over 3. I gotta cheat sometimes too. Pi over 3 and 5 pi over 3. Are those the only locations? Well, in terms of one rotation of the unit circle, yes. But what about, so I'm here, what about that? Same cosine value, right? This? Yep. This? Yep. And so on and so on and so on, right? So we have to take care of that by saying plus 2 pi n. Where n is any integer value. And I guess we should be very careful here when we say x cannot be. I'll write it up here. X cannot be those things. Don't think of this as like a piecewise type thing. I'm just like, this is kind of like a bootleg notation. I wouldn't expect you to do this in interval notation here. Yeah. I'm just asking you to what those x values cannot be. It'd be really hard to write in. Is that it? Is it the time?